All right, in the first two videos, we talked about how we can determine concavity of the function together with points of inflection. Now we're going to apply the second derivative test by using these two skills, obviously, to find a relative extrema of a function. But before we get started, here are a few remarks. So we used, in fact, the second derivative function to find concavity, to determine concavity of the function. In fact, that was the first learning objective. But we can also use the second derivative to sort of like find relative maxima and minima, and we all need a simple test for that. And it's called, in fact, the second derivative test. I'm going to give you the exact description of that in a second. And this test is based on the fact that, so if you have a concave upward type graph, let's say, and here's the point C, and if you know that C is a critical number, in fact, f prime at C equals 0, that means you have a horizontal tangent line. That means C has the relative minimum of the function. So in other words, f of C must be a relative minimum of f. And the same thing happens for concave downward type graph. Let me just quickly go through these two representative examples. So the first one is exactly what I just said. You have a concave upward type graph, and you have C to be a critical point. For that reason, f prime at C equals 0. And together with the fact that f double prime at C positive, that says that it's concave upward, right? We know that f of C is a relative minimum. So here we go. So we have the concave downward type graph, and we know that at this point here, f double prime is negative. That's the concavity of the function, which is concave downward, in fact. And we do have a horizontal tangent line here that makes C a critical number. These two information tell these two sort of like data about f, let's put it that way, tells us that f of C is a relative maximum because you make a hill here and you make a valley here. Okay, and you can tell this by just looking at f prime and f double prime and using this simple test. And here is in fact the test. Okay, so let's say like we have a function such that f prime at C equals 0, which essentially means that C is a critical number. And we also assume that the second derivative of f exists on an open interval containing C. Okay? So essentially, if f double prime is positive, then for sure we're going to know that f has a relative minimum. Okay, because you're going to make a valley. And if f double prime is a negative, then f has a relative maximum because you're making a hill. Okay, and if it is the case that f double prime at C equals 0, the test is inconclusive, so you can't really conclude anything about the relative maximum or relative minimum or neither, so you have to go back to the first derivative test and apply the rules of the first derivative test. But this is an awesome test, in fact. So once you pinpoint a critical point to test that if it produces a relative minimum or maximum, all you're going to do is to substitute C in the description of f double prime, and depending on the sign of that, you have either a relative maximum or minimum. And the unfortunate case is f double prime at C equals 0, then this test is inconclusive, as I just mentioned. All right, here is the example. So we have the polynomial negative 3x to the fifth plus 5x cubed. Well, first off, this function is continuous and differentiable on the entire real line because it's a polynomial. So we can go ahead and find f prime. So that's negative 15x to the fourth plus 15x squared. So, well, remember that we're going to set this equal to 0, so we should probably factor this as much as we can. So first off, 15x squared is a common factor here. So we have negative x squared plus 1. And now we're setting that equal to 0. Okay, so you have in fact three zeros. One is 0, the other one is negative 1, the other one is 1, because if you set negative x squared plus 1 to 0, you have plus or minus 1. So we have three candidates of x. That makes f prime 0. Okay, so now we're going to look at second derivative of the function, and we're going to evaluate the second derivative at these candidate points. So f double prime, let's use this function to go with. So you have negative 60x cubed plus 30x. Again, we're looking for a common factor. So 30x is a common factor. You have negative 2x squared plus 1. All right, so now in the next slide, I'm going to check f double prime or evaluate f double prime at 0, -1, and 1. In fact, you can pause the video at any moment and you can do this with your own calculators. And here we go. So we have the point -1, 0, and 1, and these are the corresponding y entries of those points. So you can go ahead and find those by looking at f of -1, f of 0, and f of 1, right? But that's not the point. The point is to check the sign of f double prime at -1, 0, and 1. And here we go. So the first one is positive. The second one is 0. The last one is negative. So let's look at the critical number -1 first. So at this critical number, f double prime is positive, so we do have a relative minimum. That's awesome. And unfortunately, in the second case, when x equals 0, well, f double prime at 0 as well equals 0. This test is inconclusive, so we can't really say anything about the relative extrema, okay? And in the last case, f double prime at 1 is negative, so we know by the second derivative test that we have a relative maximum. So how can we sort of like have a reality check here? So, well, go ahead and graph the function. All right, graph the function maybe for x min to be -3 and x max to be 3, just to get the full picture of the graph. And as you see that, here you have a horizontal tangent line, horizontal tangent line, horizontal tangent line, because those points are critical points. And here you can see that you make a valley, so this point is a relative minimum. You make a hill following the second derivative test, obviously. So you have a relative maximum. And at x equals 0, there's nothing, right? There's no relative extrema other than the inflection point that we can see because the concavity changes across x equals 0. It's from downward to upward. So that inflection point, in fact, doesn't spit out any kind of relative extrema. All right, now you have all the skills to start the video recitations. So go ahead and download the PowerPoint file. So the first exercise is determining the open intervals on which the graph of 8x plus 9 sine x is concave upward or downward. That's tied up to the very first video. We discussed about it, right? We check the second derivative of the function and look at the sign of y double prime across certain points that you're going to come up with. And please go ahead and start doing that. And the second example in this list is another trig function. And this time we're going to find a point of inflection that is tied up to the second learning objective. And in fact, at the end, we're going to describe the concavity. That means we're still using the first learning objective. So go ahead and sort of like try to start this example by using the first and the second learning objectives. And finally, the last example or exercise, you call it, is about the second derivative test. That is the third learning objective, but this time the function is a little bit more complicated, x over ln 3x. Make sure that you check the first derivative of the function, set it to 0, and find a critical point and test the sign of f double prime at the critical point or critical points. All right, you have 3 wonderful videos for those exercises, and please go ahead and watch them. And we are closing this section. Thanks for watching. I'll see you in another video. Bye.